Work in, work out, work in, work out, work. Okay, so the work energy principle. Kinetic energy, we said, depends on mass and velocity. Ke is equal to 1/2 mv squared. So we know that to be true. The work done on an object will change its kinetic energy, so we can also say that work is kinetic energy final minus kinetic energy initial. Let's try a problem. A 1,000-kilogram car starts from rest and attains a velocity of 20 meters per second as it travels a distance of 100 meters. So what's its initial Ke? 0, because it's not moving. What's its final Ke? 200,000 joules. Again, 1/2, 1,000 kilograms times the mass, times the velocity squared, 20 meters per second squared. How much work is done on the car? 200,000 joules. What's the average force on the car? Well, from there we have to calculate the acceleration. And from the acceleration, we can get that it was 2,000 newtons of force on the car. So, another 1,000-kilogram car changes its speed from 20 to 10, slowing down. What's its initial Ke? Well, we know that, 200,000 joules. Final Ke, only 50,000 joules. So how much work was done on the car? Negative 150,000 joules. How can you have negative work? Well, it's work energy taken out of the system. That's why we have that negative sign there. We took it away from the car. What was the average force on the car? Negative 1,500 newtons, the braking force. So gravitational potential energy. How much energy does an object have in a gravity field? Well, that depends on how strong the field is, what's the object's mass, and how high above the surface it is. So from there we get the formula PE equals mgh, or sometimes written mg delta h. Gravitational potential energy can be changed when you change the height. Increase the height, you increase the gravitational potential energy. Decrease height, decrease the gravitational potential energy. Let's try this example. Here we go. We got a plane flying. There's a mass of 2.0 times 10 to the 5th kilograms, flying at 3 times 10 to the 3rd meters. Gravitational potential energy, 5.9 times 10 to the 9th joules. Again, mg, 9.81 meters per second squared, times delta h, which is the 3,000 meters. How much work was needed to get the plane to that altitude? Well, work in, work out. Yeah, you got to put in that same amount of joules to get that plane to that altitude. Where did the energy come from? Probably jet fuel. Finally, elastic potential energy stored in a spring. How much energy can be stored in a spring? Well, that depends on how much does it resist stretching or compression. That's the K value for the string. And finally, how far is it compressed or stretched? So whatever that x distance is. So PES, potential energy stored in a spring, is equal to 1/2 kx squared. Let's try another problem. Here we have a dart gun, spring dart gun with a constant of 50 newtons per meter. The dart's loaded into the gun, the spring compresses 0.05 meters. How much energy is stored when it's compressed? 0.063 joules. How much work needs to be done to compress it? Well, work in, work out. Yeah, the same 0.063 joules. How much work will the spring do on the dart when the toy gun's trigger is pulled? Ready? Work in, work out. 0.063 joules. Same that goes in has to come out. So, summarize. Work in a mechanical system. Horizontally, when we apply a force to do work, it becomes kinetic energy if the speed increases. If the speed doesn't increase, it just goes directly to heat with friction. Work in a gravity field becomes PG if it's moving up vertically in the field. And it becomes Ke if it's allowed to fall. Once you release an object in a gravity field, it falls. Finally, work on a spring becomes potential energy if the spring is stretched to compress, and it's converted to kinetic energy when the spring is released. The dart will fly away. Well, that's the work energy principle, gang. See you in class.